Mhm.
So, good morning or good evening, depending on where you are. My name is Steve Gordon, and I'm one of the officers of the SIG-HPC education chapter that sponsors these webinars related to computational science and HPC. And uh, today we have Igor Bray, who will be talking about integrating computational science or HPC into the physics curriculum. If you could please mute while he's speaking so that there's no extraneous noise. And if you have questions, we'll hold them till the end, or you can put them in the chat window and I'll be following that for Igor to give the question. So Igor, I'm going to turn it over to you to get started.
Okay, so let me share my screen. Okay, hopefully that's working for everyone.
Yes, go ahead.
Okay. Well, thank you for inviting me to talk about our experience at Curtin. As you can see, I'm one of several authors on this presentation, and that's because I'm making the case that to do this well, you really need a substantial group of people to come together, a few like-minded people, to make these things happen. If you're not familiar with Perth in Australia, we are on the west coast where this little square is. It's a beautiful place. It's the most isolated capital city in the world. And in these times, this is advantageous because we've managed not to have any community transmissions of COVID. So it's been, we're very isolated, locked down away from the rest of the world, but things inside are not too bad. I'll be talking a bit about the Square Kilometre Array. That's going to be $1 billion largest radio telescope built. We will be building it, people from Curtin, and it's going to be located around here, so not too far away from Perth. And of course, that's very helpful for us because it requires a lot of HPC. So let's begin. So I should say up front, I'm a little bit out of my comfort zone. My colleagues who have kindly joined us know me as a researcher in atomic molecular physics, but I'm going to have a personality change here. I'm going to talk about, as an educator, I've been the head of a department of physics and astronomy for almost 10 years now. And one of the advantages is that you get to shape in what direction the department goes. But I'm certainly not used to talking about education issues to my sort of scientific colleagues, but let's see how this goes. So starting at the top, of course, these days, science and industry has a substantial HPC component. Much more so than we were students. It could be health, it could be resources. Obviously in science, chemistry, physics, it's always been there since computers came along. But now externally, our students have a large range of potential careers where HPC is the norm. And so the argument is that physics is now not just an experimental, but also a computational science. And of course, HPC is often a destination of physics students. I imagine many HPC centers around the world are staffed by physics graduates. So that's just one aspect, but various research areas where physics ought to thrive. Physics graduates ought to thrive. HPC is a fundamental tool of discovery and of understanding. And yet it's strange that I do go to high schools a lot, and I engage with high school students. Part of my job is to do outreach. And it is remarkable, and I'd be interested to hear your experience, but I get high school students always asking me, if I study physics, what job will I get? And I find this extraordinary. I've even, turned this into a bit of a joke. I sort of replied that, well, we all know that if you study medicine, you become a doctor. If you study engineering, you become an engineer. If you study law, you will be unemployed. And I say this because now statistics say that less than 10% of law students or law graduates get job in law within a year. Whereas I say, follow up, if you study physics, you can do anything and everything. And so this is my worldview, is that the world would be a better place if run by physics graduates. So I think computation HPC is important for physics. Of course, HPC is very rarely taught to science and engineering students. I've talked to my US colleagues and hear that this is certainly also the case in the United States, and for a range of quite good reasons, because there are big issues to address: who will teach it, what to take out to make room for HPC, where do you begin, how do you ensure a common background for the interested students. So through this talk, I would like to address these questions as we have had to deal with them at Curtin University. So first question, who will teach HPC? Well, presently, many students, and certainly most of ourselves, have taught themselves. And the resources are fantastic around, they really are. The documentation provided by HPC centers are just, incredible. Of course, there's online workshops, the GPU hackathons, things in pink here are hyperlinks. If people want access to this talk afterwards, they can select them. There's just fantastic resources. I really like the way they are organized at 6 HPC, where you can start for beginners right through to more experienced users. And there is really quite impressive collaboration of HP centers in education. It seems quite clear that they understand that all this fantastic computational infrastructure will remain idle if you don't educate the scientists in its use. Furthermore, access to HPC centers may be problematic. And so one of the things that we're thinking about in developing this AMP gateway is to use that as part of education, part of learning atomic molecular physics, or partly learning how to utilize HPC resources. I had this amazing experience in better times in December of last year when I was visiting NIST, the conference organized by Barry Schneider, where in front of a live audience, I opened the browser, I logged on to this AMP gateway, I took a sample input file, I submitted that job to a supercomputer, it ran, I got the output, I showed everybody in the audience the output of that run, I changed the input file, and did this 3 times, and it all worked in real time within half an hour. And hopefully nobody was overly bored, but I was able to provide a little sort of physics lesson or the way the code works. And this is possible these days, which is really quite extraordinary. And furthermore, in-house expertise rarely spans the full range of HPC. And so my sort of conclusion is that we need a mix of in-house champions with HPC access in order to put together an HPC course. And the important point down the bottom here is I argue that the physics culture is ideal for HPC education. The reason I say this is because HPC is complicated. And unlike many other areas of education, physics is not about giving recipes. And if you want to learn something complicated, You want to have a deep understanding of how things work. And so, to my mind, this is why HPC certainly belongs in physics, because the customer base has the culture to absorb the complexity and that depth of understanding required from which they can grow. So next question is what to take out to make room for HPC? Well, of course, teaching is about paying it forward. So we have to be driven by what is best for the students. From very early on, I tell my students not to set them up to have this view that you study physics just to become a physicist. So I define a success metric for a physics major, the whole degree, is the diversity of careers that those physics graduates will get. I know, of course, a lot of our students, they get their PhDs, but we know that not all of them are going to become academics. And not being an academic should not be seen as somehow a failure. So I make this point to the physics students that they should be jacks of all trades and masters of one. That physics students should be able to do everything, and then whatever opportunities come their way, then they can jump as the circumstances allow. Of course, when you're teaching, there will be many students, one physics major, and so compromise, or perhaps a better word, optimization, is inevitable. And of course, when you have existing programs, you will have people saying, no, you can't take this out. You can't have a physics major without, X. And, people will, this is a value judgment. Sometimes we will all agree that this is true for a particular X, and sometimes we will argue. And so those kind of statements can be, will come, and they just have to be dealt with depending on what X is, with the reminder that it really is what is best for the students of today. Of course, for a larger university, just creating an HPC option may be affordable. In Australia, we are funded basically for bums on seats. So we have to pay very careful attention to how many students you have in the class. And so you can't diversify your offerings if you're fairly small. So that's an issue, I suspect, in many places around the world, if not, but though I'm sure it's not the case everywhere. So the other question is how to start. And then talking to my colleagues over the last few days, weeks, it's become clear that even this very first step is not always available. And that is to have some computing courses in the early years of a physics major. This is critical. You cannot start an HP course if you're having to tell people, this is how you log into a supercomputer, this is how the Unix operating system works. All of those things must be well understood. The students must be very, very comfortable with using a computer, a supercomputer, before we contemplate parallel programming. They need to be comfortable with languages, shell scripts, all of those things need to be in place beforehand. Also, it doesn't need to be exactly a zero-sum game that you have to take something out. You can modify some of the existing things. So, as I said, I've been a head of a department for 10 years. And one of the first things I did is when I do teach an honors level course, that's a 4th-year course called Advanced Computational Quantum Mechanics. And so it had always had computational in there. For example, they diagonalize hydrogen Hamiltonian. We first did it for the atomic hydrogen, and in the last couple of years, we've even done it for molecular hydrogen as part of that course. Also, we can ask mathematicians to add numerical computation, numerical integration, solving differential equations. All of these things can complement the analytic techniques with numerical techniques. And so my statement then is that only after those preliminary steps are in place can HPC education be even considered. So some of our own experience. So Western Australia is home to the Australian Square Kilometre Array Pathfinder, Murchison Whitefield Array, and the Square Kilometre Array will start to be built next year. And of course, those facilities generate massive amount of data. And so quite some time ago, the Pawsey Supercomputer Centre was created not very far from Curtin, just a couple of kilometres from us. Joe Pawsey was an Australian radio astronomer, and because these telescopes are radio telescopes, it was deemed quite appropriate to name the supercomputer after him. And in due course, I suspect it will become one of the largest supercomputer centres in the world because of just the enormous amount of data that they're going to have to deal with. So the square kilometre is a reference to a collecting area, total collecting area of a square kilometre. And one of the things that I did long before we thought about HPC is that decided to define physics at Curtin as, I use the term multicultural, and by that I mean the culture of mathematics, the culture of computing, and the culture of physics. So, and physics has a theoretical, computational, and experimental component. And the emphasis on culture is the idea that if you get the right culture of those discipline areas, should you wish to go and specialize in any one of them, then that transition is relatively easy. And that your potential employers will recognize you as a good mathematician or as a good computer scientist or as a good physicist, and they will see that the diversity of your education, the student's education, will be seen as a bonus, as an advantage over other applicants for whatever job that may be. And so our students, this is now for quite some time, do have the necessary background for HPC, because in the very first year of their physics major, they learn object-oriented program design to get that culture of computer science. That's done using Java. They learn Unix and C programming. Clearly, so we've formally made this particular unit or a course as a prerequisite for our high-performance computing. They've learned data structures and algorithms, a course in computing, and all this in just first year. Of course, that's supplemented by Physics 1 and mathematics, advanced mathematics, whatever it might be. And the mathematicians are mostly on board. In the first year, the strongest students take the more pure mathematics, but there's applied components and computational components as they progress through their physics major. With our students being in the position of having the prerequisites to step up to an HPC course, we decided that the time was right to put it together at the end of last year. But as I mentioned earlier, none of us have the expertise across the many areas of HPC. And because of the enormous goodwill that we have at the Pawsey Supercomputer Centre and my colleagues in physics and chemistry, we came together where each one of us In fact, I didn't actually do the teaching last year. My youngest son was in the class. So I was the coordinator. We call it the unit coordinator or course coordinator. But everybody, 7 or 8 staff, did a few like guest lectures. And ordinarily, I would not have so many cooks for one course. The question is whether it will be sustainable. This is to be determined. But what I wanted in particular is for students to see the diversity of backgrounds of all of the staff who came together to do the teaching, to send them the signal that they too should consider a real diversity of potential careers. So focusing on a little detail, so it's taught as an honours subject. So in honours year, our physics students will take 4 of these subjects or units or courses, and for half of their the year, and the other half is a research project. And the way we organize it, we had 2 hours per week of content delivery. Of course, in this case, you need a lot of practical implementation time, so 2 hours for that as well. And the way we decided to assess it is through 4 assignments. We don't have an exam. We're not so concerned about students working together, not knowing exactly who did what, because by the time the students are in their 4th year, they're doing this honours level. We have examined them and tested them so many times. They're top performers. It's about them educating each other and us helping them. And so we are quite comfortable with this kind of an assessment process. And in the first year, we already had students from computing. My younger son is actually doing computer science, and also mathematicians. Physics cohort was the largest cohort, and some engineering students also attempted at the beginning, but gave up because they really didn't have the necessary background. But the engineers have also changed their courses. So now Unix and C is a prerequisite in the at least electrical engineering degree. And next year, so we had about 12 students this year, but we're expecting as many as 30 next year, given the wide interest. And so what do we do? This is my last slide. So the content is, we begin with supercomputer architecture. So we really want to explain to the students the underlying architecture of the machines that they use. And so that, we talk about the various caches, we talk about distance of travel of data to the CPUs. All of those ideas are introduced so that they have a good feel and understanding. This is not taught as a bunch of recipes of, if you have this problem, do this. If you have that problem, do that. Physicists cannot handle that kind of teaching. They expect a depth of understanding. We talk about serial optimization. So at this point, students are familiar with a computational language like C or Fortran. And we talk about elementary things in terms of how arrays ought to be stored, avoiding powers, all sorts of things and examples. We spent then quite a lot of time. We debated for a while whether we should put OpenMP first or MPI. The decision was to put MPI first because it's complicated. And because of that, because you have to start thinking about moving data backwards, forwards, coding in parallel, all of these ideas are learned and understood from the beginning. And so hence we devote 4 weeks towards that. And then on a single node, we show that, well, actually OpenMP can do a lot of that for you. And, but then talk about things like overheads of starting OpenMP threads, and when does it work well, binding to pseudodomains versus utilizing all OpenMP threads that in memory shared machines, all of those sort of issues. Then we look at GPU acceleration with CUDA, OpenAcc, OpenMP. We spend about 2 weeks on that. This is also particularly complicated, particularly awkward when OpenAcc may not be the standards for too much longer, or a standard. So this is really the bleeding edge of technology, but at least we introduce the ideas. The students know the importance of memory management, the expense associated with data transfer, and then we progress because of the large interest in astronomy data that's going to be coming in. We deal with large-scale I/O and use Python scripts and show how you can combine HPC into Python. And also containers workflows is something that we finish off with. So we ran this for the first time in 2020. It was a big success. The people who taught it last year are very keen to do so again. Many of the staff will have their research students in the courses, so it's like a win-win in that regard. And some of our postdocs also sitting in at a particular week that is of interest to them. And so I'm sure it's going to be here to stay for many years to come. So thank you very much. And I'll stop share and would be delighted if there were any questions.
So if there are questions, you could either unmute and ask them, or if you put something in the chat, I'll pass that along to Igor. Thank you. Thank you so much for your talk, Igor.
Right on time as well, just a half hour.
Hey, Igor, great talk. So this will really, I mean, I'm going to tell our department at the meeting this afternoon about the talk, and that they should look at it, watch it on when it's taped. I see one of our students is there, very good, Keegan, gets an extra plus here. The issue really, I think you hit it on the head. At least that's what we face. And that is, the problem is what to take out. And it's easy to add, but it's very difficult. And there are people, I'm sure in all departments, who will defend particular courses, until they retire. I mean, it's just they have arguments for it. And I mean, I personally try kind of what you do, and Keegan can testify to that. So can Catherine actually does. I try to put in, semi-computational extensive projects into my classes, but not everybody does that. And unfortunately, we also have the problem that the students are not necessarily prepared for that. And it is extremely difficult to get it through to the rest of the department, in many cases, I'm sure, or the majority of the department, to have these introductory courses that you're talking about. So let me just ask you, I mean, how it looks like for you guys it went okay, but I have this funny feeling that this might be a singular case.
Yes, it could be. So I've made it very clear that there's a lot of synergies. We have the SKA, we have the Pawsey Centre as a consequence. We have a culture where the people from that HPC Centre feel they must engage with the students and educate them. So we have a lot of things have come together that allow us to put the HPC part together. But it seems from what you're saying, and from what Lincoln said and Barry said, just yesterday, is that that very first introductory step is even challenging. And that I'm not, okay, so let me give you some downsides of what we've done. What we have done means the students get absolutely almost no choice in what they study. So I say it right up front that physics is going to be multicultural of mathematics, computing, and physics, but that means they're not getting a lot of any one of those. And that means that their course, their degree is filled with physics, maths, and computing. There's really no room for other things, otherwise it'll be too little, too diffuse. And this is how, so that's one disadvantage of what we're doing. But the other aspect is that our numbers were always very small when we started. And something interesting, after fighting with my senior management for a very long time, finally we've got I was allowed to raise the entry standards to the physics degree. We have an advanced physics degree. And within 2 years, our numbers doubled. So I've made the highest level maths at school a prerequisite for getting into the advanced physics degree. And I'm told by the chief scientist of Australia that ours is the only science degree in all of Australia that has highest level of mathematics at school, a prerequisite. So there are a lot of battles to be had, but one of the sort of qualities that a head of a department must have is to fight. You just have to. Otherwise you don't get things done. There's always plenty of barriers. So, and I don't know, in the US system, I guess will be rather wide and varied. But if giving students a lot of choice in the degree, that makes it more difficult to add value in that space that we decided to occupy.
I wanted to make a comment also that this issue of people appreciating the importance of HPC or of computation in general is not just restricted to, to the university. When I came to NIST, after being at the NSF for a long time and obviously very immersed in HPC for my life, I mean, I found that NIST had no culture of computation anymore. They were a leading edge institution with, very good supercomputer facilities in the 90s, and it completely disappeared. And wow. I had to spend a lot of time, and I spent a lot of time and effort trying to educate the people around there about the importance of it. And it took a long time, but, there was impact. And they're beginning to see it more and more all the time, especially in the importance of advanced computing with AI and machine learning. I mean, it's simulation too, but ML and AI are very sexy these days, so people are interested in it. But so that's the way you have to be. It's people. It's always people. It's you. It's Klaus. Maybe me. Maybe other people on this call. We just got to be determined and get in there and fight the battle. That's the way it is.
Yeah, couldn't agree more. And the other bit of good fortune that I had, or still have, is that the mathematicians and the computer scientists are very supportive, right? So there's a large body of us is working cohesively and constructively together to make things happen.
Can I ask, thank you, Igor, for the presentation. Hi. It's Anne, hi. Can I ask, so with the first run of the course, is there, I don't know, lessons learned or something that you want to do different in the subsequent conducts of the course coming out of that analysis of the first course?
Yes, because of its success, we expect a lot more students in the future. And so we have to modify our assessment tasks so that they weren't such a big pain to assess. So for example, the last task was, so once only, not in the future, was to use any part of the course and show how it would enhance your honours project by the things that you have learned. So you can imagine the diversity of things that came to the poor person who then had to go and mark that. So I said to that person, look, very nice, but let's change that. How about you simply assess that which you have taught? So it's that kind of thing. The other aspect in terms of assessments, to make sure that they're readily reproducible from year upon year. So these aspects of GPUs, what we realized is that we're really, in that particular part of the course, we need to have a lot more hands-on. There's a lot of diversity in the GPU. In due course, perhaps next year, things will stabilize. Maybe we'll only use OpenMP. I think you need version 4.5 onwards to manage the GPUs. And if that sort of stabilizes, we will focus in a little bit more. And then, but we're on that bleeding edge, and things will change. And we will need to become a little bit more efficient. But it was good enough. And it will get better.
Okay, thanks.
Well, I would say that the arguments that you've had in terms of what X to take out of the curriculum is very common in not just in physics, but across all the sciences and engineering that are interested in computational science. And I know there have been various other attempts to integrate it. So I know there have been a number of programs that have just added sort of a minor in computational science as sort of an add-on. But that means that students need to take extra credit hours, and that means that also that the numbers of people that you affect is probably pretty small, because not that many students want to burden themselves with extra credit hours. And the other thing I think I've observed is that as more and more faculty use computation as parts of their research, the arguments become a little bit easier as time goes on. But I hope it doesn't take the retirement of everyone who doesn't use computers before this can actually happen.
Yeah, no, that's a very good point that I didn't make. Yeah, go on, Barry.
Just a quick question. Yeah, I know this is just, I think I know the answer, but I'll ask it anyway. The issue of the students being prepared when they get to the university, it's my impression that US students are just less prepared than students in Europe and other places in the world to jump into this stuff right away. You have any comments on that?
Look, it's a tricky one. What we find is that students really struggle with fundamental concepts in computing. So at school, everyone's done some maths, everyone's done some physics, but computing, coding is, they see, most students, not all of course, see it for the first time. And even the top physics students struggle with some of the concepts that they learn. So what I explain to them when I greet them is that real physics is not going to start until the second semester. So the first year physics will be more about getting everybody on the same page. But I'm saying to them, those of you who will be taking object-oriented program design, you will struggle. It will be difficult, but in the end, you will find that the physics students will be the top students in that course. You just have to work really hard. Those of you who will take advanced mathematics, because you've done higher level maths at school, will find that transition challenging. And for those reasons, we will not have physics at a high level at the beginning. By the time they come into the second semester, they now have, the culture of a university life. hopefully developed a necessary work ethic to progress, and we start to ramp things up in physics as well. So it is critical to have students in large numbers, or sufficiently large numbers, that are prepared to go on to that HPC step. And just come back to the point Stephen made about having academic staff research well aligned with HPC, absolutely that was a critical component of building that team. So the chemists were those chemists who did a lot of HPC, and the physicists were all of the ones who were engaged in that space. Yes, that's made our life a lot easier because we didn't have to fight this removal of X's in our particular case.
One of the things I've observed for the summer programs at NIST, which bring in both high school and undergraduates, is that a lot of students know things like MATLAB and Mathematic in some cases, but you ask them about C or about Fortran and they don't have a bloody clue. Mm-hmm. You know, Python, you know, Anaconda, whatever. They know all that stuff, but what they don't really learn is what is, you know, you say, how do you solve a second order differential equation with boundary conditions on a computer? You know, well, you know, they can tell you, well, we go to MATLAB and you use this, it's and this, but if you ask them the details, they don't know anything. So
Barry, sorry, you're breaking up a little bit. I don't know, it's for me or everybody else as well. Yeah, so sorry, Barry, I didn't hear the last part.
I mean, this problem has to do with what is being taught again in computer science departments. I mean, they don't teach Fortran anymore, right?
Well, it doesn't have to be Fortran either. It could be C++ or whatever, but
yeah, that's right. But that's right. So they are, I mean, Python, I see that now, you know, I get assignments and, you know, a lot of stuff comes back in Python, right? And if I'm lucky, and sometimes I can't do anything at all. Let me ask you, but I really have two comments. So one is, or questions, and I should almost know the answer given that I have visited Australian universities so many times. But how about your, how intensive are your general education requirements? Because one of the things, of course, you know, you mentioned a bunch of things that you would do and then add mechanics and things like that. If we did this, there would be no class in, I don't know, whatever they have to do. Keegan can tell me all the things that our students have to do that have absolutely nothing to do with their major in this case, right? So when I was in Germany, educated, right, I studied physics, and that means you must take some math, some chemistry, and that is it. I never took any course outside of that. But here, you know, a large number of our courses in the US are general education courses, presumably to fix up the high school system, right?
Well, I don't know if it's to fix it up, but it's because I think there's a very different culture. It's a very different culture, the way you educate students in Europe, and I'm sure Australia as well, from what we do in the US. And I'm not trying to make a statement as it's better or worse. I'm just saying it's different. And you know, in the US, if the students don't want to spend this additional time, and a lot of them don't or can't, then you know, it's a problem.
Yes. So in our case, we have one unit in the entirety of the 4 years that is a general communications unit. It is not well regarded. Its approval rate is very low, but we have limited, in fact, I would say it this way, even though this is being recorded, I'm very glad that its approval is very low. That means we're not going to get more of them. Right? So we constantly have to, so when I go to schools and I advertise what it is that we have to offer, I talk about it's maths, it's computing, it's physics together. And we have to deliver what we advertise. Right? I don't advertise that you will do the communication unit. Right? That's a compliance activity. So absolutely, you have to, I mean, the way you phrased it is that you're trying to fix up the school education system. Well, it becomes inefficient that way, right? And we talked about this just yesterday, that some of the US students are taking 5 years to complete the ordinary degree before they go to graduate school. And of course, that's expensive for all concerned. The whole thing about mass education is that efficiency is important. That's what it's about. Well, it's a component, sorry. You know, you want to do things efficiently.
I mean, I don't want to dominate the conversation, but let me ask you another thing then, somewhat unrelated, and is for universities, especially smaller universities like ours, for example, right? It would help a lot if you guys made your material available in some form, you know, as you know, I mean, some big universities, you know, they tape their quantum courses and things like that. So do you have any plans of doing that? I mean, maybe not right after the first time, but after you run the whole thing, you know, for 3 years, will you do the most horrible thing and write a book,
well, first of all,
or something?
The issue, it's available immediately. You go to my atom.curtin.edu.au/HPC. So what we did in the first semester is immediately available to all. All of us used the HTML on that web page because using university systems to rapidly change things is impossible. So we just did our own thing, and so it's all available to everybody. But I should, and again, emphasize that the HPC centers, and you just look at SIG HPC, that link I have over there, their things are presented beautifully. Ideal for a person who unfortunately did not have an opportunity to be taught, but is keen to teach themselves. So the resources are out there, and you're most welcome to look at what we have done. But it's the people. You have to have the like-minded champions, the cooperation. So for example, we needed access to machines with GPUs. So we talked to our Pawsey colleagues, they created reservations for us. Our students would be able to log in, don't have to wait to submit their jobs, all of those things. There's a lot of logistics, we all know. There's a huge amount of logistics that have to be dealt with when you're going to a laboratory with, if you want to do HPC. You want to have quick turnarounds, you want to get sensible error messages, all sorts of things. And so this is something, we needed that oversight of our Pawsey colleagues, making sure everything works. And so it's a big team effort. But I should also just flag this because I'd like to, because Barry mentioned to me a while ago that, in the United States, you have difficulty attracting suitable people to these HPC centers who have the skill set to provide support to others. And this is where teamwork is so important. And I talk about engaging in partnerships with HPC staff. So I have a number of papers published that have HPC staff as co-authors because they're really engaged with us on the science and enabling it to happen. And that really creates a win-win for all concerned because it really builds that motivation of it's not just you in the sort of back room helping somebody else to do great stuff. You can be part of it. And I think that's also a help to motivate people to this area if we develop those kind of partnerships. And in fact, Pawsey is going to have a program in the near future where they will co-fund postdocs. And so we'll have a postdoc that's sometimes embedded at the Pawsey Supercomputer Centre, sometimes in the science group. And again, just getting that good communication going between people will really lead to very good outcomes.
And if I can put in a plug for which Igor and Klaus are well aware of, we're three of a number of others who are trying to develop or are developing a science gateway for atomic and molecular physics, in which a lot of these things we hope will be part of that project, if the NSF decides to bless us with some money.
Yeah. Well, Anne here is the representative of the Pawsey Centre. I'm delighted that she's joined us because just yesterday I was talking about how we could try and get some letters of support and engagement from Pawsey, because this, as I said, there's a huge amount of goodwill all around. It's just we're the jigsaw puzzle pieces, and we just need to know how we can all fit together.
Well, let me thank you again for the presentation. Let me remind everyone here that within the next couple of days, we will post both the presentation and the slides on the SIG HPC education site, and the session will also be on YouTube then. So that's sighpceducation.acn.org. If you're not, by the way, this is my last plug here. If you're interested in these topics, the SIG HPC education chapter is only $10 a year to join. And we tried to have a large number of these kinds of conversations with scientists and engineers and HPC centers around the country. And we'd love to have you join so that you can find out about these things and also contribute. So that's my one plug here. So thank you again, Igor, for your presentation. And thank all of you for attending, and wish you all a well rest of the day or night, as the case may be. And thanks again.
Okay. Thanks to you, Steve, for
Thanks,
putting
Steve.
this together.
Talk to you later.
Thanks, Igor.
All right.
Okay. Good night from me.